Hello, and welcome to the first lecture for Unit 2, Constant Velocity. Now to start our lecture today, we're going to do some definitions because we want to make sure that we are all speaking the same language. So we have 5 different words here, and we're going to start with initial position. When I say initial position, what I'm trying to describe to you is your starting location. Because it's a position, we're going to use the lowercase letter x as the symbol for it. But we want to be more specific. We want to tell everyone that it is the initial position. So we'll use the subscript of I. So initial position is xi. And the unit for this is going to be in meters. If initial position is starting location, then final position must be your ending location. And because it is still a position, we're still going to use a lowercase letter x to talk about it, but we are going to use the subscript of f to denote that it is the final position. And we are also going to use the unit meters for this. Now, displacement. Displacement is the straight line difference between your final position and the initial position. It sounds a lot like distance, but it's not. We'll go over what the differences are between distance and displacement. But first, you should know that the symbol for displacement is delta x, and it is also measured in meters. So if we look at the differences between distance and displacement, we'll tell a little story in order to show those differences. Let's pretend that we are here at Verona Area High School and it's lunchtime, and so we want to go and get some lunch over at Melio's. So to get from the high school to Melio's, we first need to drive north on M. Then we need to take a right and head east on Cross Country Road, and then we get to Melio's. So for the sake of this example, I'm going to make these distances very easy distances. We're going to say that we went 3 meters north, and we're going to say that we went 4 meters east. I know that that's not really how far you would have to go, but let's make it easy. If I asked you the distance that you had traveled to go from the high school to Melio's, you would have told me that the distance is 7 meters, right? You had to go 3 and then you had to go 4. 3 plus 4 is 7. Displacement is talking about the straight line difference from where you start and where you end. So our displacement is this. It's the hypotenuse of this right triangle. And if you remember from math class, a right triangle with legs of 3 and 4 has a hypotenuse of 5. It's a 3, 4, 5 triangle. So our displacement is 5 meters. The big takeaways you want to get from this is that distance counts every single step that you take. The path matters for distance, but for displacement, we only care about where you start and where you end and the difference between those two things. It's not going to pick it up. There's something else that I would like for you to know about displacement. Displacement is what is called a vector. A vector is talking about something that has both a magnitude and a direction. What do I mean by magnitude and direction? Well, let's look at our example again. The magnitude is really just trying to describe to you how big something is. So the magnitude of this example was 5 meters. And then if I told you what direction you had to go, maybe to get to Melio's you have to go like northeast east on a compass rose. Well, now you know the direction that you have to go. And those are the 2 pieces of information that displacement will give you. Let's do another example, though. Let's use a number line, just like how we did in your lab. So we'll have the positive numbers on the number line, on the right side and the negative numbers on the number line on the left side. And just like in your lab, let's have a little car. So our car is going to start at the origin of our number line. So our car is going to have an initial position of 0 meters. And we are going to make our car drive to the left until it gets over here to a final position of -3 meters. If I ask you what is the displacement of this car, well, to get the displacement, we have to take the final position minus the initial position. So we would have -3 meters minus 0 meters. So our displacement is going to be -3 meters. So let's look at the pieces of information that were given there, right? Here, the 3 meters is our magnitude. It's how big the displacement was. But then right here, this negative sign, that negative sign is trying to tell you the direction. On our number line, the negative numbers were to the left. And so if you notice, we moved to the left. And so that's showing up here in this negative sign. So positives and negatives are going to be very, very important in this class. Positives and negatives are going to tell you what direction you are moving. Let's do another example. All right, so let's set up another number line. And we're going to keep the same thing, right? The positive numbers were on the right, negative numbers were on the left. And let's have our car drive to the right. So we'll have him start where we were before. So now my initial position is going to be -3 meters. And let's have him drive to the right. Perhaps he'll drive all the way over here to a final position of 2 meters. Now if we look at this, we can clearly see that, hey, he went to the right and he went 1, 2, 3, 4, 5 meters to the right. Let's calculate the displacement and see if our calculation shows us the same thing. So we're going to do final position minus initial position. So we will do 2 meters minus -3 meters. And 2 minus -3, that's the same thing as 2 plus 3, gives us 5 meters. So did our magnitude match up? Yes, 1, 2, 3, 4, 5. That's also what we calculated. And then we went to the right. And to the right was towards the positive. And we can see, even though we didn't write a positive sign, we do know that that's +5 meters. Okay? So that's how displacement really gives us a lot of information. It's a vector that gives us the magnitude and the direction. Let's continue these definitions with velocity and speed. So velocity is the rate of change of position. We're going to use the lowercase letter v to symbolize velocity, and velocity is measured in meters per second, right? Change in position per change in time. That unit really tells you what this value is trying to describe. Now, this also sounds a lot like what we would have used as the definition for speed, right? The rate of change of position, how fast is your position changing? That sounds like speed, how fast you're going. But there's one difference. Velocity is also a vector, just like displacement. But speed is not a vector. It is what is called a scalar. So velocity gives us that two pieces of information. It tells us how fast we're moving and what direction we are moving. But speed is missing the direction piece. Speed only tells us how fast we're moving. That's what scalars do. Scalars only tell you magnitude. They don't tell you direction. So speed can be thought of as velocity without direction. It is also symbolized by the lowercase letter v, and it's got the same unit, meters per second. So now let's start looking at some graphs. One thing that I would like you to remember is that in this class, we're always going to have time on the x-axis for all of our motion graphs. That's how we did it in the lab, and that's how we're going to keep doing it here for the rest of class. So if we flip the page of the notes, let's draw a generic position versus time graph. So as long as we have time on the x-axis and position on the y-axis, we can make this graph look however we would like. So maybe my graph looks like this. We want to be able to get key pieces of information out of these position versus time graphs. And we talked about how we can read these pieces of information when you did your lab. It was what we wrote about in the analysis part of your lab summary. We talked about how the slope of a position versus time graph tells you the velocity. It tells you velocity and not just speed, because if we look at that slope, maybe it's 3 meters per second, the 3 part of the slope tells us the magnitude. But this is a positive slope that I've drawn here, and so I know the direction that we are moving in. We must be moving in the positive direction. If this was a negative slope, then I know that I'm moving in the negative direction. So the fact that we know the direction means that I know velocity out of this slope and not just speed. The other thing that we get out of this is the y-intercept, and the fact that the y-intercept tells us our initial position, which is a very key piece of information that we want to know, right? We want to know where we start, and looking at the y-intercept of a position versus time graph will tell us that. So if you look at your lab, you guys wrote an equation for this line. You wrote something like position equals, maybe it was 0.5 meters per second times time plus maybe it was 1 meter. Your numbers might be a little bit different, but this is kind of the generic, this is what we looked at when we wrote the equations for our lab. Now this equation draws the straight line from this graph here. But the problem is that this thing only works for your specific lab. Right? As long as we have a car that moves at 0.5 meters per second, and as long as we start that car at 1 meter on our number line, then we could make predictions about the position of that car at any future time, which is great. That's what we want to be able to do. But what if we don't start it at an initial position of 1 meter? Well, then this equation, as it's written right now, no longer works. So what we need to do is we need to come up with a way to generalize this equation. And instead of using specific values, we want to have kind of like a general thing that we could put in there that would be able to allow us to use that equation for any situation at any time. So let's rewrite that equation from your lab using nothing but general terms. So for position, we're going to write that the final position. And then right here with our slope, we know that the slope of this line told us the velocity. So instead of writing 0.5, I could just write the velocity, whatever our velocity might be for this car, multiplied by time plus our y-intercept, and we know that our y-intercept is our initial position. So we'll just write out a generic initial position. This equation is going to be the backbone of almost all the algebra that we will do in this whole unit. In this unit, as long as I give you the initial position, the time, and the velocity, you would be able to calculate the final position. I might even be able to give you the final position, initial position, and the time, and you would be able to tell me the velocity, right? So whenever you want to use algebra as a tool to solve a problem, this is the algebraic equation that you'll use. And just really fast, we can actually write this equation a little bit more concisely. Because if we subtract xi from both sides of the equation, we end up getting that xf minus xi is equal to v times delta t. And we just saw this on the previous page, right? xf minus xi is the same thing as delta x. So we could write that displacement is equal to velocity times the change in time. And this is often how you'll see me write the equation, just because it's a little bit more concise. But don't be thrown off. These two things are the same. All right? Good luck.